Hello, uh, everyone. Thank you so much for joining us today for the Canadian Underground Infrastructure Innovation Center's next webinar. Today we're going to be discussing some new changes to the 6th edition Handbook of the PVC Pipe Design and Construction. I'll be your moderator. My name is Kyle Vanderwolf, and I work with IPEX. I'm the Regional Engineer for Municipal Products for Western Canada. And yeah, let's get to it. We have some good, exciting stuff here that's going to be brought on by Brooks Ryan. I'll be presenting him a little bit later on here. Here at the CUBIC Academy, it is organized by the Canadian Underground Infrastructure Innovation Centre at the University of Alberta and Venture Media Inc. CUBIC Academy offers classes, courses, webinars, and events to further elaborate on our underground infrastructure educational opportunities across Canada. When it comes to the webinar series, the CUBIC Academy happens every third Thursday of the month, and so please join us for our next installment, which is going to be on artificial intelligence in geotechnical engineering. For a full list of any kind of upcoming and past webinars, please visit cubic.ca for more information. When it comes to registration here, we do have some exciting news for our upcoming CUBIC Safety Academic Academy on September 16th and 17th. So registration is open and it's going to be happening in Edmonton, Alberta. So please do check out the cubic.ca website for more information on that. And thank you to this webinar series sponsors, Ackerman, for helping promote and get these webinars going. It's every sponsor is very important, and we appreciate every assistance that comes our way. I'm going to be now kind of moving you toward our speaker here, Brooks Ryan. He is a regional engineer for Univel with the PVC Pipe Association. He covers the western region of the United States and Canada. And in his current role at Univel, he provides technical support to PVC pipe users and those interested in learning more about using PVC, as well as participates in industry standards organizations and assists the utilities, as well as engineers in updating their specifications related to any sort of PVC water or sewer piping. He has received a Bachelor in Science degree in Mechanical Engineering, as well as Mathematics from the Southern Methodist University in Dallas, Texas. Let's hear it for Ryan, Brooks Ryan here, and look forward to his presentation.
Thank you, Kyle. I appreciate it. As Kyle mentioned, I'm with the PVC Pipe Association. We were a little brief background on us. We were founded in 1971 as a nonprofit organization. We're the industry trade association, and we're the authoritative source of information on PVC pipe. We serve the engineering, regulatory, public health, and standardization communities. And as Kyle kind of mentioned earlier, that predominantly what we do is we provide support, design help, any information to anybody wanting to learn more about PVC pipe. As part of that, we release a handbook, so we recently came out with our 6th edition in December of this past year. A little history on that. The 1st edition of the handbook was published in 1977. As of 2001, there was over 65,000 copies in print, and the 5th edition was published in 2012. So the 6th edition being published in 2023 or 2024, my apologies, was a long time coming, about 10 years. They usually get updated once every about 10 years or so. So yeah, currently on the 6th edition, 3 chapters are available free of charge on the website. And that's all choose your own chapters. So if there's 3 chapters on there that you're interested in and you don't necessarily want to buy a full copy yet, you can always download 3 free chapters. Some of the most common ones are usually installation, design, and some of the specific topics as well, like installation specific applications, stuff like that. We did add 3 new chapters here. The last 3 chapters, chapter 15, health and safety, chapter 16, sustainability, and chapter 17, asset management. All 3 of those are new to the 6th edition, as well as a number of updates that were done to the existing chapters. A number of tables were moved to the appendices, and we'll kind of be getting into that, as well as a brief summary of each chapter. And so to start us off with chapter one is kind of just a brief introduction chapter, to what is polyvinyl chloride pipe. So it includes a brief history of PVC pipe and an overview of the material properties. As kind of a brief history, the first PVC pipes were manufactured and installed in the early 1930s in Germany. PVC pipe came to North America in the 1950s. I think first installation was 1954. The AWWA and ASTM standards for PVC pipe developed in the 1960s and 1970s. The first C900 standard came out in 1975, with C905 coming out in 1988. And of course, C905, I don't think that got discontinued in 2016. Actually, that all was rolled into C900. But it is kind of cool to go back and see when that originally came about. And so now currently C900 covers 4-inch through 60-inch pipe. And there are over 1.5 million miles of PVC water pipe in service across North America. So across the US and Canada today, there's approximately 1.5 million miles in service. And I apologize here. So there was a little bit of formatting error on the title. I think that's my fault. I have an older version of PowerPoint. But chapter 2 focuses on the raw materials and the material properties of PVC. So it gets into the PVC material and the chemical properties. In this chapter, the major changes, there was more of an in-depth description added for the what is the polymerization process for resin, as well as additional discussion on compounding of PVC material and material cell class codes. So kind of as a brief background of that. The resin itself, that's a product of natural gas and salt, and I think historically the handbook really had not touched on to what goes into that material and to what actually that is. But with people getting more and more concerned with PFAS chemical stuff like that, we felt the need to include a more comprehensive bill of materials in there of what's actually going into the pipe, so that everybody knows. You don't have to worry. There's none of those bad chemicals per se going into the manufacture of PVC pipe. We also get more into the hydrostatic design basis and stress regression. So those are the qualities used to determine longevity of PVC pipe. So there's kind of a picture down there that's it's all a test-based data, and it's basically a cyclic test that's performed up to 10,000 hours that's used to determine that to determine that hydrostatic design basis, where you then can use that to determine a pressure class and what wall thickness you need to meet certain pressures and stuff like that. We've also delved more into structural properties, impact strength, tensile strength, and modulus elasticity in chapter 2. And then, of course, there's been a number of longevity studies and hydraulic research studies done since 2012 that we felt the need to include in Chapter 2, just again to provide a more comprehensive background for the material. Chapter 3 gets into resistance to aggressive environments. Couple major changes that happen in this chapter: the chemical resistance tables for PVC have been removed and replaced with references to more comprehensive tables and data found in different documents, PPI, TR19, and ISO or TR 10358. So these PPIs, the Plastic Pipe Institute, they have had a comprehensive study done on chemical resistance to different plastic pipe materials. Our tables were dated, and we felt it was better just to point to their tables as they've the testing that's been performed for that has been significantly more comprehensive. We do still have chemical resistance tables for gasket materials. Those have been updated to be current and moved to the appendix just to make the chapter a little more concise. And then some additional topics were added to this chapter, including resistance to environmental attacks such as seismic events, ground movement, flooding, and wildfires. Chapter 4 gets into manufacturing and testing of PVC pipe. This really chapter is a description of the PVC material, again, what polymerization is, and an overview. Or I guess this chapter used to contain that overview of material and polymerization. Most of that was moved to chapter 1, as I kind of mentioned earlier. This chapter now focuses a lot more on the qualifications and quality control testing procedures. So just as a brief overview of those, qualification testing generally is what's used to determine pressure class, what's used for design of PVC pipe. So that gets into testing to determine cell class codes, which show modulus elasticity, tensile strength, impact resistance, stuff like that. Health effects, that's done in accordance with NSF 14 and NSF 61 to make sure it's safe for drinking water. Hydrostatic design basis, as I mentioned earlier, this is established through long-term hydrostatic pressure testing. And this establishes the stress regression line, which you then can calculate a hydrostatic design basis out of. Joint performance testing. The gasketed joints are subject to specific hydrostatic pressure, both internal and internal vacuum pressure testing. And then, of course, there's sustained pressure testing done periodically to 2.1 times the pressure class for 1,000 hours. Quality control testing is more of this is a series of tests more so to ensure that the pipe being produced is of quality. That includes the burst pressure testing. That's done at 3.2 times the pressure class for about up to 60 to 70 seconds. The extrusion quality tests, this is where samples of pipe are immersed in an acetone solution for a certain amount of time, and when removed, there shouldn't be any flaking or cracking or disintegration, and this really is a test of extrusion quality. The impact testing, that's kind of self-explanatory. Generally, a metallic cylinder is dropped from a specified height on a ring cut out of pipe, and it's ensured that there's no cracking or damage or anything like that occurs. Flattening. The flattening test requires PVC pipe sections to be flattened to 60% of the original diameter without any damage. I believe the percent kind of was, at if you're flattening the pipe fully, nothing's going to flow through there anyway. So it's kind of a unrealistic test because it's functionally pointless. So 60%, a test up to 60% of the original diameter was seen as low and all that. And of note there for PVC pipe action limit. So you definitely have a design limit well under the point that the pipe is tested to. Stiffness, pipe is tested for the pipe stiffness is tested to ASTM D2412, and then the hydrostatic proof test. This is the dwell test where the pipe is pressure tested. Each section of pipe is pressure tested to 2 times the pressure class when coming off the line. Chapter 5 gets into design of pressure pipe and fittings. There was a handful of topics kind of added to this chapter. There's a new section on cyclic design that was added, as well as an overview of new methodology for cyclic lifespan calculations. Really, the overall existing pipe standards, pressure system types. So that talks about, gets into the working pressure check, checks for recurring surge, occasional surge, and cyclic capacity. And so an example of that would be, for checking for working pressure, you obviously want to make sure that's lower than the pressure class. Same with recurring surge. There's methodology to calculate for that. And then for occasional surge, PVC has a built-in 1.6 times the pressure class occasional surge allowance. Cyclic capacity, of course, there's that new methodology to calculate the lifespan for. And then the design examples used were updated to kind of be better and more comprehensive examples. Pressure fittings were also included. I believe the old handbook did not include design of PVC pressure fittings. External loads on buried pipes. So this chapter has been reorganized. There wasn't a whole lot that changed per se in this chapter. There was a better emphasis on design practices and differences between designing with rigid and flexible pipe materials. And this isn't really this is purely educational. And the main difference really is that for rigid piping materials, the pipe itself isn't isn't using the surrounding trench for support, and so the majority of the soil and external load weight is being supported by the pipe material itself for rigid pipe. For flexible pipe materials like PVC and ductile iron, the pipe slightly, has that flexibility there that allows it to use the soil arch to support uh, the pipe. So that force downwards from the external load actually is being distributed throughout the soil surrounding the pipe with flexible pipe materials. And you might notice I did mention ductile iron as a flexible material. That is, from a physics standpoint, considered a flexible piping material because it does have that same mechanism that PVC does, where it can slightly deflect uh, and use and distribute that external loading to the soil surrounding it. So it's just nuances between designing with the different types of materials. You have to take in different things into consideration regarding the trench width and stuff like that. Um, Prism load tables have been removed. That was something that took up a number of pages in the old handbook. We've kind of tried to make this edition more concise. It's been replaced with references to software for external load calculations. If you do really like the Prism load tables, I believe we still have the old edition of the handbook available. And in that chapter, there should be 5 to 10 pages of example Prism loading for different soil depths, different live loading like HS20 or railway loading, E80, stuff like that. And then, of course, there's different sections in this chapter on earth loads and live loads. So there are still tables for railway and truck loading and stuff like that that get into live loading and the different depths at which that's really relevant. Chapter 7 gets into design of buried pipe for external loads. So this kind of builds on Chapter 6. This focuses a lot more on how to design for flexible pipe systems. This is a lot more, how to actually design with the pipe. The previous chapter, Chapter 6, is more of a broad overview of design considerations and the pressures at different external loads and stuff like that and depths. So this chapter it's into pipe stiffness, which is the inherent ability of flexible pipe to resist deflection under load. Time lag, which is that length of time from installation of a pipe to when the pipe deflection is essentially complete. So when your settlement is functionally completed and all that, gets more into the pipe soil interaction and the varying ways to calculate that, as well as performance limits. Some of the big ones for PVC. Reverse curvature occurs at 30% deflection. That's when the pipe begins to kind of bow inwards. And again, as mentioned earlier, the design limit for deflection is 7.5%. That 7.5% limit contains a safety factor of 4 to that reverse curvature. And so that reverse curvature, that 30% deflection, isn't a structural failure point. That's just when your flow calculations aren't really going to work. You're no longer going to have a nice round interior section of the pipe because it starts to bend inwards at that point. Ring buckling, there's a section that's been added on ring buckling, and this may also govern the design of flexible pipes under conditions of internal vacuum or potential underwater installation or maybe loose soil burial. It's not a huge consideration in most cases, and usually, but it is still something to check, especially if you're designing a force main or something that might experience internal vacuum pressures. And then design life. There's a bit of design life explored for this chapter as well. Chapter 8 gets into installation-specific applications. So these discuss directional changes, temperature effects, thrust restraint, stuff like that. So some of the things that were changed, the biggest change here really was with regards to longitudinal bending tables. We recently, the industry updated the AWWA C605 installation standard for longitudinal bending. The old version showed DR18 8-inch pipe in DR18 and lower pressure classes, so thicker walled pipe to be bent, and that's been removed, not due to any real issue with the pipe, but because stipulations were added for the amount of force required to actually perform that bending from an installation point of view, and it was determined that you might need mechanical force to actually bend pipe that is greater than 8-inch at DR18, DR14 thicknesses. and generally it's recommended that you use manual force only when you're bending that pipe. So again, it's not any structural issue or any issue with the pipe material itself that caused that change. It's more of a consideration of ease of installation, practicality drove that change. So that's really just been updated to match C605. And I'll note that requirement or that stipulation is different for PVCO because of the thinner wall. It takes less force to bend the same sizes and pressure classes as for PVC. So that is slightly different, and we'll get into that in the PVCO chapter. Section on temperature effects was added for derating factors, for correction factors, for specific calculations. This is really mainly a consideration during installation and during bending. Again, because that changes the forces required during bending. But again, once the pipe is buried, generally speaking, below 1.5 to 3 feet of depth of cover, temperature normalizes a lot, and you're really not going to have much issue experiencing higher elevated temperatures that far underground. Thrust restraint, we did revise the section on thrust forces, thrust blocks, and mechanical joint restraint. And then, of course, there are still sections on support spacing, filling and grouting annular space, and buoyancy and flotation. Hydraulics, there was a handful of changes added here, actually, just to kind of get into what the chapter goes into depth on. It goes a little bit more into depth on hydraulic radius. So talking about the value of the hydraulic radius varies with the flow and is obtained by dividing the cross-sectional area of the flow by the wetted perimeter of the pipe. What that means really is the perimeter of the pipe in contact with the fluid that's flowing. So for pressure pipe and fittings, you can generally use either the Hazen-Williams or Darcy-Weisbach equations. Generally, we refer to the Hazen-Williams equation because that's kind of the most common. That's the C factor that everybody's familiar with. And one thing that I think people that isn't often considered is that the C factor is variable, actually, depending on certain conditions and flow velocities. Most of the time, it's fixed in standards and specifications at a certain value. The general industry recommendation for PVC is a C factor of 150. A number of recent testing has been performed confirming C factor of 150 being conservative for PVC. Most of the recent testing and even old testing that's been done has shown a C factor ranging from 150 to 165 for PVC. For non-pressure pipe, the Manning equation is the most used, and field and lab testing show that the Manning's N for PVC is anywhere between 0.007 and 0.009. Generally, the industry recommendation is 0.009 just to stay on that conservative side. And again, ring deflection, some people ask, is ring deflection going to reduce that flow area? And generally is not an issue, even at that 7.5% maximum deflection design limit. Your flow capacity really is only potentially reduced by up to 1.9%. So generally, it's not a huge concern, especially considering most of the time deflection is designed at 5% or lower. So very rarely, even if you're designing for 7.5% deflection, are you going to hit that point with proper installation. Chapter 10 is on general construction. There were very few changes to this chapter, so I'll kind of just briefly recap it. The chapter goes over storage, handling, receiving pipe, inspection and unloading recommendations, trench best practices, stuff like that. Brief section on joint assembly, pipe embedment and backfill, ground movement, field testing, and then operations and maintenance. But again, this chapter, a lot of the installation and construction chapters haven't really changed between the last few editions, just because there really haven't been any new installation practices that have come up over time. Chapter 11 gets into pressure pipe design and installation, and some new sections were added on, more details were added with regard to appurtenances, such as valves, fittings, hydrants. More information was added on directional changes, such as for bedding and angular deflection. And actually, most of those details were moved to Chapter 8, but it did add sections on PVC sweeps and pressure fittings, and ductile iron fittings, of course, are also compatible with PVC. Thrust restraint was moved to Chapter 8. Branch and service lines were kind of expanded on, and that these can be as large as size-on-size taps, as long as the tap is done correctly and uses the correct appurtenances to make the connection. And of course, for disinfection, PVC pipe is not affected by disinfection products when proper practices are followed. Generally, we don't get that question very often, but occasionally somebody's concerned with chlorination and stuff like that. And actually, if anyone is wanting to learn more about tapping, we do have a separate tapping guide that goes even further in depth with regards to proper tapping procedures and best practices. Chapter 12 gets into non-pressure pipe installation. And so the trench construction here was actually moved to Chapter 8 because that trench construction recommendations, those are very broad and apply to both pressure and non-pressure piping. There's a little bit of expansion on appurtenances such as manholes and manhole connections. There's additional information added on service laterals, especially with regard to installing risers, cutting connections, and those laterals. And then, of course, inspection and testing. Generally, there's a handful of different inspection and testing procedures for non-pressure pipes, such as visual inspection, cammering, and the like, leakage testing, and deflection testing. The most common used form of leak testing for non-pressure pipe is low-pressure air testing, and I do want to stress on that. This hasn't changed between editions, but that the max pressure allowed for air testing is 9 psi. That's because air is a compressible fluid, and so generally you can get a lot more instantaneous forces coming out of lower pressures when using air, when pressurizing with air, which is kind of a safety concern more than anything else. Mandrel tests, those are the deflection testing earlier, and generally those are performed after a minimum of 30 days to allow for to have occurred. Trenchless installation. This chapter has been expanded on as well with new technologies that have kind of come about. There's a number of ways. There's a number of joining methods for PVC that are conducive for trenchless construction methods. So those are internal mechanical joint restraints, such as gasket, specific types of gaskets that have internal restraints, pin and groove gasket joints, spline lock gaskets, spline lock gasket joints, and butt fuse joints. Casings and tunnels, casing spacers, push and pull through installation is something that's very doable with PVC. This is probably one of the most common ways to trenchlessly install PVC pipe is with these casings and using casing spacers. One major consideration when you're doing that is for grouting. The heat of hydration does need to be considered. And one way to mitigate this is to fill the pipe with water during that grouting process. The same thing goes as if you're doing open cut and using flowable fill or encasing pipe in concrete. You do want to take into consideration the temperatures that heat of hydration can kind of cause and get to. Horizontal directional drilling, this is another common method for trenchless installation. Really the main consideration when using PVC for HDD is the bending and pullback forces. And then, of course, slip lining is also possible, both in the segmental and continuous. Some forms of trenchless joining for PVC are kind of more conducive for segmental, and some more so for continuous. The main difference segmental is when the pipe is installed one length at a time, so it's kind of cartridge style. You can drop it into the trench footer and then install it section by section as that pipe is continuing to be pushed or pulled through the casing or the liner. And then for continuous, that's when the pipe lengths are assembled first in a large section and then installed in one long string. Pipe bursting is also possible with PVC and kind of follows that similar, some of the similar installation methods above, such as HDD and slip lining. And then for structural liners, there are PVC structural liners out there. We, as the association, don't really get into those, but there are some fold and form style PVC liners out there, both structural and non-structural, that have been used for rehabilitation and such. Chapter 14 is on PVCO, molecularly oriented PVC. This chapter is really a brief overview of what PVCO is, the different properties, the standards and testing, and specific design applications. To anyone that's not familiar with PVCO, it is the same starting stock material as PVC. The cell class for PVCO starting stock is the same as for PVC. The main difference is that PVCO has been molecularly reoriented by stretching the pipe post-extrusion. And so properties such as impact resistance, modulus of elasticity, fatigue resistance, and short-term strength have been improved through this process. PVCO for pressure design, because PVCO has a HDB of 7100 psi, you can get a thinner wall or you can have PVCO at the same pressure class as PVC, but with a thinner wall. Is functionally what that means. But there is one kind of key difference when you're designing for pressure applications, is that PVCO has a modulus of elasticity of 500,000 versus PVC having a modulus of 400,000. So the surge pressures are going to be different for PVC and PVCO for the same change in velocities, and that's definitely something to consider. We do have a table and formulas for that in Chapter 14 of the handbook that go over that. External load, it's the same design considerations as for PVC. Pipe stiffness for PVCO, because of that different modulus and different wall thickness, is going to be different than for the same pressure classes of PVC. We do have tables for that still in the chapter, so that is, again, just something you want to check if you're designing a force main and concerned with external load or something along those lines. Generally, we only see PVCO used in pressure applications. I don't think we see a lot of it used for gravity sewer. So external load's not as much of a concern, but again, with force mains, you might occasionally have sections that are unpressurized for periods of time. Health and safety, this is a new chapter. This gets into PVC raw materials, the ingredients in PVC. The primary ingredient in PVC is PVC resin. There are additional ingredients added during the manufacture to either enhance or modify specific properties. The majority of these additives are also utilized in many common applications, even household products. So some common ones are paraffin wax, which, for example, is used often to coat fruit and vegetables. Calcium stearate is used in a lot of medications, supplements, and candies. Titanium dioxide can be found in some sunscreens. It is it's actually a very common household one. It's like a Tums. That is pure calcium carbonate. Safe, common additives. None of these are really cause for concern. The resin itself is made from salt and natural gas. Vinyl chloride monomer is used to produce PVC resin. It's a gas that's polymerized into PVC, but it is not created during the manufacture of PVC pipe. And actually, NSF 61 tests for VCM and PVC pipe, and consistently results from these tests have come back non-detect throughout the years. It's also worth noting NSF 61 VCM limits are 1/10 of the US EPA limit. So the NSF 61 limit is a very, very conservative limit, and even when they're testing for it, they consistently come back non-detect. So not even is it shown below the limit, it's not found at all. Construction sites, brief section on safety during construction has been added to this chapter. So discussion of safe practices for field cutting, air pressure testing. As I mentioned earlier, it has a pressure maximum of 9 psi when conducting air pressure testing, water pressure testing best practices, and then tapping best practices as well for pressure pipe. And then other health sections have been added, such as on common chemicals that people are concerned with in the water industry that are not used in the manufacture of PVC. So some common ones are lead, mercury, phthalates, and BPAs, and then PFAS obviously being a big topic for today's kind of world. And these chemicals, none of these are actually used in the manufacture of PVC pipe in North America. These are kind of common questions we get people concerned, and just we wanted to explicitly state, show what material actually goes into the pipe. These materials aren't used in North America for pipe manufacture. And NSF 61 does test for those other ones as well. That's not something that they limit their testing to. And again, consistently, even though it's not used in manufacture, it comes back non-detect. Sustainability, this is a new chapter that's been added as well. It gets into longevity of pipe. It also kind of goes back over that brief history of PVC being used in North America since the 1950s. Testing on pipe in service for up to 50 years has shown PVC pipe can be expected to last for more than 100 years. Embodied energy is the total energy required to manufacture, transport, and install and operate a system. This kind of gets touched on as well, because a number of years ago we had a LCA conducted, a life cycle assessment, which gets into a variety of different qualitative environmental factors, such as embodied energy, CO2 output, recyclability, stuff like that. And an EPD is kind of hand in hand with a life cycle assessment. The environmental product declaration is based on that LCA. And these are kind of like bills of health or bills of materials, or almost like food labels for a product. It shows the different environmental values and emissions and stuff like that that are associated with the manufacture and use of a product. And we have this data published all in that chapter on sustainability. And there's some discussion as to why that's important and why that's something that you can take into consideration when designing or specifying material. Asset management, this is a new chapter as well. This really is just a very broad overview on asset management, a brief section on what asset management is, why it's important, that it can assist in prolonging asset life, improve decisions about repair and maintenance, and help set expectations regarding water system conditions. This also gets more into service life as well, talks about specific studies that have been performed on PVC. Most of these are dig-up studies where old pipe's been dug up and tested against new pipe standards. And I wanted to mention one in particular. There was one done in 2018 as part of a series being done by EPCOR. That's Edmonton Public Utilities. And the 2018 was done on one of the first PVC pipes installed in Edmonton. It was about 40 years old, and it was done by Doug Sargent. And he published that in a number of conferences, AWWA and ASCE conferences. And it showed that the pipe tested to new pipe standards. There were so they tested that old pipe to present standards used for new pipe production and found that there was no issue. It tested as if it was new. I included some of the data on that. And actually, I think, oh, there it is. It was, I believe, the only issue was the one sample had a minor defect during flattening. But again, the pipe being buried, you're not really going to experience that flattening or crushing, especially not to the extent that the flattening test is required. The major, components for design considerations are going to be, pressure, extrusion quality, joints, stuff like that. And so he actually published that paper at the 2018 ACE conference and showed that the samples passed all the new pipe quick burst requirements, joint pressure testing, and extrusion quality tests. And then that was actually part of an older series too. EPCOR had been doing tests on that same section of pipe in 1994 and 2005 as well. The flattening tests, extrusion quality tests, and burst tests, and it passed each time throughout that process. The 2018 test, actually, one of those sections of pipe had been frozen solid and thawed and tested new pipe standards as well, which was kind of cool. His presentation from just a testing. A brief overview of what they are Appendix A to metric conversion values. Most of our values throughout the handbook are in English Imperial listed. Appendix B show dimensions for PVC and PVCO. Appendix C is a list of standards for PVC and PVCO pipes and products. Appendix D gets into chemical resistance of PVC gasket materials. As kind of mentioned earlier, that used to be in the resistance to environmental factors chapter, but that was moved to the appendix as it's several pages long and it felt more concise that way. The chapter kind of reads a little smoother. And then Appendix C gets into support spacing forces and requirements for PVC pipe as well. Other than the handbook, we do have a number of additional resources available. On our website, there's a member directory, technical resources, and a contact form if you do have questions. We do have a number of other documents we publish under these resources and FAQs. So these are a number of tech briefs that we put out on frequently asked questions that are common enough that we felt the need to put out 1-page to 2-page documents on these common topics. We do also publish a number of guides and research reports out there. The force main design guide is very specific to force mains and actually gets more into cyclic lifespan and cyclic life design, as kind of mentioned earlier during the pressure design chapters. And that was actually new to the handbook as well, because the new cyclic formula that was developed by Utah State University, that came out, I want to say 2015 or 2016. And that kind of expanded on previous research and contained a whole lot of new research on cyclic testing and lifespan based on number of cycles and pressure fluctuation during these cycles and stuff as well. Mostly it's important during force main design, but it is applicable to other cyclic designs as well. If you're in an area with high pressure fluctuations or a lot of occasional and cyclic surging and stuff like that. So I cover the West. There's a lot of mountains. You often do see a lot higher amounts of cyclic surge and stuff like that in these more mountainous regions and areas where you need a lot more pump stations to operate a system. Also, there's been new studies for hydraulics and for deep bury as well. These have both been done kind of as case studies on existing pipe that's been tested just to confirm existing factors and that the design values used are conservative. We do also have a number of calculators. We have calculators for cyclic life based on that report earlier I mentioned, an internal pressure design calculator and external load calculators. We have several others as well, on such as on hydraulics, and I believe we're publishing one on sustainability as well pretty soon. Other than that, if you do have any additional questions, I'm happy to take them now, or if there's none that you can think of, feel free to reach out and contact me or any of the other engineers we have. We're all happy to help, and we're all, collaborative. We all work together. So there's no, even if you're not in my region per se, I'm more than happy to help answer any questions that anyone has.
Fantastic. Thank you so much, Brooks, for that presentation and all the wonderful information that you've provided us. There have been currently one question in the queue here. It's actually a two-parter, and so I'm just going to read out the first question if you're ready for that.
I'm ready. Sorry.
The first question is, per installations aside HDD, is there a guideline for design/installation by DSPT, in brackets, example, direct pipe method?
I don't know that there's a particular design guide for that. I know a lot of the time it's manufacturer to manufacturer, because the different trenchless products available for PVC do differ from manufacturer to manufacturer. And often the applications that these products can be used for differ as well. So, for example, some of the locking gaskets cannot necessarily be used for installation via pushing, but can be used for pull-through, while some others can be used for both pull and push, stuff like that. And so there is definitely differences between the different types of products. And so it is usually kind of best to ask each manufacturer when it comes to specific trenchless methods of installation.
Thank you. Thank you. On the second question, it is regarding the materials. With the movement to ban plastics in general because plastics ending up in the food chain, can it be deemed that PVC may not fall into that category of microplastics ending up in the water?
So actually right now there's a number of testing being done both by Utah State on microplastics and PVC, as well as by the state of California. So I cover California and kind of tuned into what is going on over there recently. If anyone's not familiar with it, they passed a bill basically requiring all utilities eventually to conduct microplastics testing so they can kind of cut down on the amount of microplastics in their water system. They do not expect any of it to be coming from the PVC. The sources they were most concerned with were tires, clothing, external infiltration, stuff like that. Their initial data is supposed to, I believe, start coming out next summer. And there's a lot of utilities there that's part of this pilot program for testing that contain a lot of PVC in the system. One of the big ones is Irvine Ranch Water District. I think they have about 1,000 miles of PVC of pipe in their water system, and another 1,000 miles of recycled water mains that are PVC. And I don't believe they expect to find many microplastics coming from the pipe itself. As an aside, I believe University of Toronto is also doing microplastics testing on water systems, both with a focus on material and PVC-centric utilities, as well as non-PVC dominant utilities, just to see the differences, stuff like that. So far, we haven't seen anything. We don't really expect there to be really microplastics coming from the material itself. There's been a number of dig-up studies done that inspect the interior of the pipe and show there's been no degradation over time, no material that's really shedded over time, and that kind of indicates that we shouldn't really be seeing a lot of microplastics coming from the pipe material itself. Recently, there was one done in conjunction with our hydraulic study that we put out. It was done on I think it was C900 installed in 1977 or 78, I want to say. And it was a portion of it was dug up and sent to a lab that did inspecting of the inside of the pipe, and they determined that the interior of the pipe it had the same markings that new pipe usually comes off the extrusion line with, and it based on that they are concluding that because there's been no degradation or abrasions in that, there really shouldn't be any material shedding off that pipeline throughout its service life and all that, or at least not any noticeable quantities. But yeah, that is definitely a topic that I think is going to be more and more widely researched in the future. But we're not necessarily concerned as far as expecting there to be a lot of microplastics associated with PVC pipe use.
Excellent to hear. Yeah, I do want to say that I think it actually is maybe mentioned a little bit in the LCA as well, on that topic. But
yes, yeah,
currently
you're correct.
We are still waiting for a few more questions to emerge. So I have a question for you, since we're kind of waiting a little bit to kind of go on the topic of testing. You know, and there's lots of universities kind of looking at different testings, that type of thing. What's next in the books for Univel for when it comes to testing, and publications? What's currently happening in for the future?
Yeah, there's a handful of testing that we have going on currently. Presently, one of them is a series of cyclic testing done for PVCO. So historically, there's been a number of cyclic tests done for PVC pipe. That's what's been slowly used over time to develop the cyclic life calculations used for PVC pressure pipe. But for PVCO, there's not been a whole lot of comprehensive testing done, enough to the point where you can formulate an equation or set of values for a cyclic lifespan of PVCO. So one of the things that we're kind of working on right now is getting testing done with UT Arlington to conduct that cyclic testing for PVCO pipe to hopefully establish an equation or series of data points to use to determine lifespan of PVCO in cyclic applications such as force mains or areas that have a lot of pump stations and high pressure cycles and stuff like that. We do expect it to be generally, our recommendation historically has been to treat the cyclic life of PVCO the same as for PVC of corresponding pressure classes. We do kind of expect it to have, based on some European studies and Australian studies that have been done, a higher cyclic capacity for PVCO, just because of the higher modulus of elasticity and higher tensile strength. But again, that's, we can't definitively say that till we have concrete data, and so that's kind of the point of the testing. We're also conducting scratch depth testing. There is a gouge or scratch depth allowance in the C900 and AWWA standards, and we just wanted to conduct testing to confirm that. The existing allowance is 10% of the wall thickness is allowed to have a scratch or gouge of concern, and so we just wanted to confirm that, or even, if it's see if it's overly conservative, and is it something that's maybe not as big of a concern if it's a little deeper than that. But that we have that going on, and then as I kind of mentioned earlier, this isn't our test, but the Utah State University works closely with the water industry as a whole, and they're conducting microplastics testing right now, actually. That hopefully, I don't know when they're going to publish, but they're doing that on PVC, as well as a series of tests for specific utilities as well, to see levels of microplastics in utility systems as well. So,
wow, it's wonderful to hear that there's so much testing going on. I look forward to see those results. I guess to continue, there is one question here that was asking to maybe elaborate on some of the new information in Chapter 5 with regards to the cyclic design. So it sounded like there was some new research that came up. What changed exactly?
Yes. So as I briefly mentioned, I think when I showed the force main design guide, the main change here was the old handbook did not really make reference to a specific cyclic life calculation, or a way to calculate the number of cycles till failure. That was all kind of based on general cyclic testing and kind of a best guess. So the new methodology was developed by Dr. Folkman of Utah State, I believe in 2014 or 2015, and was based on a series of cyclic testing that he performed at their Buried Structures Laboratory, basically to determine a baseline of data points that he could then use a best fit line to come up with a formula for number of cycles till failure, and use that to calculate then use that formula to methodology for cyclic life calculations. So that's all been included in the new chapter, and we also have a calculator that is based on that. And generally the gist of that is you're taking a handful of variables into consideration. So the number of cycles your system experiences daily, the pressure fluctuations, so the change in pressure from the lowest pressure to the highest pressure, and what your ideal design life is going to be, and you're kind of plugging all that in to these series of formulas, and his direct formula basically gives you a number of cycles to failure, which you can then use or compare with the number of cycles you're going to experience every day, and then just see how many cycles or how many years till that might potentially fail. Generally, it's not an issue. Most of the time, we see we see design out there as conservative when it comes to cyclic design and force main design, especially with the thicker walls like DR14 and DR18. But it is something that's worth checking if you're designing force main or in an area that has a high level of cycles and a lot of cyclic pressures and surge pressures and stuff like that. And again, this is all stress that this is specifically within, specifically referencing cyclic pressures. So reoccurring surges, stuff like that. Occasional surges, like in power failures, stuff like that, or flooding, stuff like that. Occasional surging is not really taken into consideration because it is not a repeated strain on the pipe. That's something that there is a 1.6 times pressure class allowance for occasional surges, and so that's not necessarily included in this new methodology because it's not as something that's as relevant to fatigue.
Perfect, thank you. Another question here: do any of the changes I imagine this is referring to the handbook, suggest it would be prudent to examine any previous designs or installations?
Not that I can think of. Generally, no. That was one of the things I wanted to stress with, I think it was on installation, maybe. Longitudinal bending. That was really the only thing I can think of, but that's not really something that needs to be addressed for existing installations, because again, that was not a change that the limiting of longitudinal bending to certain sizes or DRs was not something done because of any concern of pipe structure or anything like that. That was done strictly due to concerns with the amount of force required to bend thicker pipe in larger diameters, because it would functionally be impossible to do with manpower. It would be something you'd need to use mechanical devices for, and potentially would present a safety hazard towards workers or something like that if that pipe were to snap back and somebody was in the trench or something like that. So again, that was the main consideration for that change, but it's not really a issue. If you've longitudinally bent 8-inch or 12-inch pipe that's DR18 or DR14 and it's already been buried and installed, that's not something that you really need to be concerned with. It's that mainly is if you're actively performing installation, you want to stick to those recommendations, those new recommendations. But that's due to a safety thing for installers. That's not really a pipe issue.
Perfect.
And sorry, I kind of stumbled over my words there on that a little bit, but I just wanted to stress, you can't stress that enough, that it's not indicative of failure, or it's not, your old pipe that you've already done that for isn't going to fail necessarily. It's more of a present, consideration due to practicality and construction.
All right. This question here is, Is there any published research or data that shows performance of the different types of gasket systems available, such as SBR or nitro or EPDM or any other?
There has been, I believe the gasket manufacturers themselves publish data on performance when they can. Some of them have conducted studies and stuff like that. I know that we don't have a ton on the specific performance of gaskets, other than that generally they're expected to last the lifespan of the pipe. And again, we do have those chemical resistant stables for gaskets. These are generally pulled directly from the gasket manufacturers, and those kind of just get into, there are different chemicals and the potential contaminants that will affect different gasket materials in different ways. So nitrile, for example, is going to be the most resistant to hydrocarbons. SBR and other materials might not be as resistant to hydrocarbons, but might be more resistant to certain other chemicals, stuff like that. So it's all one of those things that if you're concerned with chemical contamination, you do want to check the tables. Generally, the one that most people I feel like are concerned with is hydrocarbons, and generally nitrile is more than sufficient for that. I will note these gasket materials are the same for all gasket pipe materials. So ductile iron, PVC, everybody uses the same gasket materials generally. It's not something that's necessarily different pipe material to pipe material.
Mm-hmm. But we are getting close to the end here, so I'm going to ask this question, and we'll see if we can maybe squeeze in one more. So this question does come up regularly, and they're asking, so what are the requirements for storing PVC outdoors, and how does UV exposure affect the pipe?
Yeah, so that's a great question. That is something we get asked a lot, especially I cover the Southwest as well. So Arizona, Southern California, Nevada, that is a big topic there, and of course Canada I know can get pretty warm too. I was up in Calgary last summer, and it was beautiful weather, but some days were kind of surprisingly warm, to me coming up from Texas. But generally, as long as the pipe is stored within, is used within a 2-year time limit, the industry recommends that you shouldn't be leaving it outside for more than 2 years. It's generally fine. If you are concerned with UV exposure or outdoor storage, you can wrap the pipe or cover the pipe with some kind of light, opaque tarp or breathable fabric. You do want to make sure it's a breathable fabric and it's a light color. Darker colors can trap heat better. There was an instance in Arizona of somebody that had left a bundle of pipe outside under black tarp for like 2 years or something, and it did change shape because it was, summer out there can get 120, 125 degrees Fahrenheit, and trapped under a black tarp, it can, almost hit 200 in some cases, and so it is kind of an extreme case, but it is, just goes to show you do want to, light colored fabric, breathable fabric is more than fine, or a non-oil based paint if you're using PVC for outdoor applications, can help prevent any UV exposure. UV is not really a huge issue. Sun fading we have people ask about, and generally that lightening of the material, the white color that kind of takes place, if you were to scratch the top layer of that, it would be the same original color beneath. That color is meant for identification, not to hold over time per se. So blue pipe, the blue is just there to let you know it's water pipe. It's not a color that, if it fades to white, is necessarily an issue.
No, thank you. In your guys' testing, as just adding on to this question, I think there was in your Univel testing, it had a pipe that was for 10 years exposure and everything passed performance. So the 2-year limit, that's just kind of like a general recommendation. That's not a hard, fast rule.
Correct. Yeah, I believe the pipe that they tested, I think they left it on a roof in either Texas or Arizona for 10 years and then came down and tested it. And the only change in properties they found was a slight decrease in impact resistance, which is really a construction consideration more than anything else. You want to make sure you're not dropping rocks or shovels or equipment on the pipe, but you would preferably not do that anyway. And generally, once it's buried, there's no impacts that are going to be occurring since it's underground, and theoretically, you shouldn't be experiencing impacts
Perfect.
either way.
Well, I think we've hit our time limit here. So, thank you so much for your presentation, and thank you to everyone in Kewick here, and as well the audience for attending this seminar. I hope everyone learned something and got a little new information out of it.
Yeah, thank you, Kyle, and thanks everyone for attending. If anyone does have any further questions, I mean, I'm happy to take emails, calls, any of that. So thank you again.
Great. Thank you.